All right. Great. All right. So I'll turn my camera off and give the podium to Joe.
Thank you. So can you see my screen?
Yep, I sure can. Looks perfect.
Okay, great. So how will I know if someone wants to ask a question?
Oh, that's a really good point. They could just come off mute and chime in and interrupt you if that's okay with you.
That's fine with me. And if it's going to be a long question, I might defer it to the end. My goal is to speak for maybe 40 minutes, if that's okay, and then just leave time for discussion at the end.
That is absolutely perfect. And I will try to pay attention to the chat, but I'm not too good about that. But so if somebody wants to put a question in the chat and not interrupt, that way I'll do the interrupting.
Yeah, I find it hard to monitor the chat while I'm speaking, so I'll expect people to speak up.
Okay, sounds fantastic. All right, thank you, Joe.
Sure. Okay, well, I'm Joe. I am a senior math stat at the Census Bureau. I've been at the Census Bureau for, I think, about just over 11 years now. And before that, I was a faculty member at Penn State University. And what I'm going to talk to you about today is a package that I've written called cvam. It's an R package for modeling coarsened categorical data. So cvam is something like an acronym for coarsened variable modeling. And I'll tell you what that is in just a moment. I am going to assume that because this is an R Govies group, that most people are familiar with R. You don't have to be a super R user, but I'm going to be showing lots of R code. I won't be explaining it all, but you should be able to get the gist of what I'm doing, even if you're not super familiar with R, just as long as you've had some basic experience. For example, if you know how to run a regression in R using LM, or a generalized linear model running GLM, then if you know those things, you should be able to catch on pretty quickly to the syntax of my package. Just a little note about versions. The cvam package is available from CRAN. If you go there, you'll see the latest version. The current version that's up right now is 0.9.3. The results from this talk today were produced with version 0.9.4. I think it should be exactly the same as 9.3, but just for transparency, this was produced with a version that is not yet up on CRAN, but that should be available within a couple of days. I haven't submitted it yet, but from the time that you submit to the time it appears, it's usually a matter of a day or two. So you can look for the new version early next week. There is a major update coming. It's going to go to version 1.0 point something, and I'm hoping to get that out next month. And that's going to have some new names for some of the secondary package functions. So I'll just tell you the reason why I'm doing that is that this talk is based pretty closely on a paper that I wrote and submitted to a journal. And that's now being revised to be resubmitted. And the editors asked for some changes to some of my function names and a few other minor changes to just how the package is set up. And so some of the secondary functions, their names might change and the syntax might look a little bit different. But the two primary functions in my package, the coarsened function and the cvam function, will remain basically the same. So just in the future, if you download something new, you'll check the notes to see what has changed. So this is an outline of what I'm going to talk about today. And just to be complete, I forgot to give my disclaimer that the views expressed are those of the presenter and not necessarily those of the Census Bureau. Okay, so coarsened data. Coarsened data is a term that you may or may not have heard before, but it's a notion that generalizes missing data to include values that are partially observed. So the most common area where this happens in statistics that people know about is survival analysis. You can have observations that are left censored, meaning that you know that they're bigger than something. right censored, meaning they're less than something, or interval censored, which you know that they're between something and something else, but you don't know the exact value in any of those cases. The underlying variable in survival analysis is usually a continuous time to event. What I am going to be talking about today is coarsened categorical data. And these coarsened categorical variables pretty commonly arise when you're forming variables, say from combining multiple items on a questionnaire, each of which has missing values. And then when you combine them on a questionnaire, if you have a case that's missing one item but has the other one, or vice versa, you know that it falls within a subset of cells in the two-way classification, but you don't know the exact cell that it falls into. And so when you're doing that kind of recoding, you can very easily get cases with partial information. This also comes up when you're trying to harmonize information from multiple data sources that measure similar phenomena, but perhaps at different levels of detail. And so I'll give you a good example in just a second. And here it is. This is a data set that I pulled off from the General Social Survey. It was the 2000 General Social Survey. And there were about 1,300 participants. And here I'm classifying them by two variables. There's a race variable that comes up as white, black, Hispanic, or other, or a missing value. And then there's Hispanic origin, non-Hispanic or Hispanic or a missing value. Now, one thing that you'll notice is that race is missing for about half the cases. And it's missing that much because that question was given to a randomly selected half sample. And so it's missing about half the time, and those values are missing at random because they're unrelated to the underlying values. The other variable, Hispanic origin, was given to everyone, but it is missing part of the time. Now, interestingly, you'll notice that Hispanic comes up as a category of race. And the reason why that happens is that this race category allowed you to answer white, black, other, or write in something. And quite a few people wrote in Hispanic, Latino, Latina, and something like that. Not a lot, but a few people did that. And when they did, you could classify them as Hispanic. And so that's what I did. I coded them as Hispanic. But if you were missing Hispanic origin, if you're missing race, you do know the Hispanic origin most of the time. But if you're missing race, obviously you're missing race, and that creates problems if you want to combine these. So suppose you want to create a race Hispanic origin variable with 4 levels, and let's just say we want to set them up as non-Hispanic white, non-Hispanic black, non-Hispanic other, or Hispanic. So a 4-class variable. So basically what you're doing is you're taking, if you think of the race as having 4 categories, Hispanic origin as having 2 categories, there's 8 cells in that table. You're classifying them down. So everybody in this cell goes into 1, everybody in this cell goes into 2, everybody in this cell goes into 3, and everybody in this cell, these 4 cells, or this cell, actually that cell is a 0. You can't have anybody in that cell. So anybody in these 4 cells goes into class 4. Now, this one white person who's missing Hispanic origin, that person could belong to category 1 or category 4. You don't know which one. And that's not a problem because it's just one person. However, these 1,300 non-Hispanic persons with missing race, they could belong to categories 1, 2, or 3, but you don't know who they are. And you don't know where they are. And if you throw away that important information that they're not in category 4, and you just treat them as if they're missing values, you're going to have an analysis that's grossly inefficient and also will be pretty badly biased. And I will show you evidence of that in just a second. Now, a question just came up if they if these slides will be distributed, and the answer is I'm happy to distribute them. So Wendy, I'll talk with you later, Wendy and Donna, about how to do that. Or you can contact me. I'll give you my email at the end, and I'll be happy to send it to you.
That sounds great. Thank you, Joe.
Okay. Okay, so here I'm showing estimated proportions falling into those 4 categories, along with standard errors computed by 2 different methods. The first one is what I call a complete case analysis, which treats those partially observed data values as missing values. So I'm going to ignore the fact that those 1,300 people who are missing race, but we know that they're non-Hispanic, I'm going to ignore the fact that we know that they're non-Hispanic and just set them to missing, and basically throw them out of the analysis. The other procedure is a maximum likelihood procedure that treats them as coarsened values, takes into account that partial information, and retains everything. So these first 2 columns here show the estimated proportions, and you see that there's a huge discrepancy in the Hispanic column, or the Hispanic row. The maximum likelihood estimate is about 7.5% in that category, but complete case basically doubles it to 14%. And there's a huge inflation in the standard error when you throw out those cases. So with all of the partial information, the standard error is about half of a percentage point. With the complete case method, it's about 1 percentage point. So this complete case method really is not doing well. It really suggests strongly that you should be retaining that partial information. So this package that I wrote is called cvam. And if you have worked with R, you probably know that categorical variables are called factors. And a factor is basically an integer variable, taking values 1, 2, and so on up to however many categories there are in that categorical variable. And if you see 1L, 2L, that L just means it's an integer value. And although it's an integer, there are character strings attached to these variables, so that when you tabulate them, you get those character strings coming up as the labels associated with those categories to make them easier to interpret. So a factor is just basically an integer variable, a discrete variable with probably a small number of categories. What I do in cvam is I extend this factor class to store categorical data that can include arbitrary types of coarsening. So I can store values where you know it falls into category 1, 2, or 3, but not category 4. So I can take that extra information into account and store it. My software also allows you to fit log linear models to these coarsened factors. And it provides functions for summarizing and comparing models, computing predictions, imputing missing values, and so forth. Now, if you don't have coarsened data, but you just have missing values, I can handle that too. So this is an excellent tool for handling categorical data just with ordinary missing values. And if you work in a government statistical agency, I'm sure you have lots of categorical data with missing values. And this is important because there are very limited options out there for handling categorical data with missing values. The only other package specifically designed for that purpose is a very old package called CAT, which interestingly I wrote about 30 years ago when I was little more than a teenager. And later on, someone took it and ported it into R. When I wrote it, there was no such thing as R. And so someone else has been maintaining it. I haven't been using it. And for over 30 years, that pretty much was it. There wasn't anything else available for doing, say, log linear modeling with missing values. This new package cvam supersedes CAT. And so if you are using CAT or are tempted to use CAT, don't switch to cvam because it's much better. Okay, now I'm going to talk about coarsened factors. Coarsened data is the general term for observations that may be fully there, fully missing, or somewhere in between. And instead of seeing the random variable's actual value, we are told that it lies in a subset of the possible values. So for example, if you had a continuous variable, I'm not dealing with continuous variables today, but if you had a continuous variable, types of coarsening would be, if you're told that this VI is equal to a specific value, then it's fully observed. If you're told it's between 0, if it, you know it's positive and it's between 0 and A, then it's left censored. If you know that it's between B and infinity, it's right censored. If it's between A and B, it's, sorry, that's a typo, it should be interval censored. And if you don't know anything except that it's positive, then it's a totally missing value. Now, if you have a variable like this, you can't store it as a floating point real number with a single missing value code. You need to carry around more information, but most statistical packages, including R, aren't built for this to be done automatically. The theory of coarsened data can be thought of as an extension of the theory of missing data. The two major references on this are Hitchin and Rubin and Hitchin back in the early 90s. And the concepts from the theory of missing data do translate to coarsened data. For example, there's a term called coarsened at random, which is basically the generalization of missing at random. Now, some areas of applied statistics have their own terminology for special types of coarsening. For example, non-informative censoring and survival analysis, but the ideas are essentially the same. Today, I'm going to assume coarsening at random, and I'm going to ignore the coarsening mechanisms. Someone came up with a question. Stata has a concept of interval regression. Yes, and I believe that is a good example of how one package does have some features for coarsened data. In that case, as a regression outcome for continuous regression.
Hey Joe, since you were addressing the chat, I have a question. So,
Sure.
so if you were trying to sort of rank order, and I'm trying to remember this because this was something Tommy Wright was doing, and I think he was trying to rank things, like rank states or something. But the way you had the intervals there made me think of his approach to the ranking problem. So is that relevant at all? I mean, could your approach, I know it's kind of vague.
That's a good question. If you can reduce a variable, say a rank variable, to partial information where, say, you know, say you're ranking 51 states, so the ranks can be between 1 and 51, and you have an observation where you know its rank is greater than 10, but you don't know what it is. I guess that's an example of coarsened categorical data. But maybe that'll become pretty clear when I set up the notation in just, I think that's another slide or two.
Yeah, thanks. Maybe I'll try to just make a note to remember to go back and look at what Tommy did, and then
Okay.
See if there's any connection.
My guess is probably not a strong connection, but I could be wrong. Okay, so here's a little bit of notation. So remember that I told you a factor in R, which is a categorical variable, takes integer values 1, 2, up to however many categories you have. So let's imagine a categorical variable J for individual I, whose true value lies within a set 1, 2, up to however many categories you have for that variable. So this pound sign just means the number of elements in the set. So this is a funny notation, but I just did it to avoid having to introduce extra symbols for how many levels you have for a variable. So it's it's not a great notation, but it saves on symbols. So these levels for the underlying categorical variable, if there was no coarsening, are going to be called base level codes. These are what you would see the values that you would see if there was no coarsening or missing values. Now, instead of actually observing this V, suppose you observe something which I'm calling V star, which is a coarsened version of V. And the possible values of this coarsened one lie in an expanded set. So this expanded set has all of the levels in the original, the underlying true value, plus some extra ones. These extra levels here that I'm tacking on the end are I'm calling them coarse level codes. Now, if V star is one of these base level codes, then it's fully observed, because you're just then saying V star is equal to V. So if V star is equal to 1, then you know that V is equal to 1. So this 1 value maps onto 1, 2 maps onto 2. This maximum base level code maps onto this onto itself. However, if you have observed one of the coarse level codes, then you know that the true value lies within some subset of the base level codes, which I'm calling a mapping set. So if V star is equal to a particular value V star that is greater than one of the base level codes, that doesn't tell you the exact value of V. It just tells you that V lies in some mapping set, which I'm calling M of V star. So you plug in V star and you get a subset of the base level codes. So that mapping is a one-to-many function that maps elements of V star onto non-empty subsets of V. And I'm sorry, there should be a subscript J there. Sorry about that. Now, as your number of base level codes grows, the number of possible coarse level codes that you can imagine becomes huge, because basically what you're saying is any possible subset of the base level codes could form a coarse level code. So it's, if you have a true variable with 5 levels, you could have 2 to the 5th minus 1 possible coarse level possible codes for the coarsened value. In practice, you don't need to use all of those possible ones, because many of them won't actually occur in the application. So you only need to work with the coarse codes that actually happen, not ones that you could imagine happening in some alternate universe. And by convention, I'm going to use the last coarse level code to denote a traditional missing value. So if your coarse value is the highest, the maximum coarse level code, then I'm just saying that the mapping maps to all of the base level codes. So it's just one of the base level codes, you just don't know which one. So that's a conventional missing value. So to create a coarsened factor in my package, there is a function called coarsened, which will do it. And the basic syntax is you have an argument, a first argument, which is a factor that you want to convert to a coarsened factor. And then the second argument is a levels list, which is a named list that specifies the coarse levels and what their mappings are to the base levels. So if that sounds complicated, the simplest way to see what's going on is to show you a trivial example. Okay, so here I'm creating a little categorical variable with 1, 2, 3, 4, 5, 6, 7 observations. The observations are red, green, missing value, yellow, not red, green, not green. So if you just turn that into a factor, then R treats it as a factor with levels green, not red, red, yellow, and then a missing value. So R thinks that it has just 5 categories. Now, based on the names that I've given you here, it looks as though red, green, red, and yellow should become the base levels, because those are not combinations of everything. It appears that not green is an observation that means it could be red or it could be yellow, but it's definitely not green. The not red is an observation that could be green or yellow, but is definitely not red. And NA is a traditional missing value, so it could be green or red or yellow, and you don't know which of those three it is. So this is how you create the Coarsened factor. First, you need to attach my library, and then you would say my Coarsened factor gets a coarsened where the first element or the first argument is my fact. So it's just this factor here that you created. And then the second argument is the levels list that basically gives the mapping from the base level codes to the coarse level codes. So this is a list. The first element of this list says, I have a coarse level code called, which I'm labeling as not green, which is a combination of red and yellow. So that's the mapping. Not green maps to red and yellow. And then I have another one, not red, which maps to green and yellow. And then I do have a third one, NA, the missing value, which maps to green, red, or yellow. But you don't have to give that because this Coarsened function will sense that by default. Okay, so once you do that, you look at this Coarsened factor, you see that you have observations that look like what they were before, but now you have different attributes. Before, the attributes were just those 5 different levels, but now you have 3 base levels, you have 2 coarse levels, or sorry, 3 coarse levels, not green, not red, and missing. And then you have this mapping which says what each of those coarse levels maps onto in terms of the base level. So not green is a combination of red and yellow, not red is a combination of green and yellow, and NA is a combination of all the codes. So that is my Coarsened factor. So what is this thing? This thing is a factor. Actually, it's an enhanced factor. It's a factor, it inherits from a factor, but it has this special class called Coarsened. So it is a factor, but it is also a Coarsened factor. And it has a levels, which includes the base levels and the coarse levels. So if you ask for the levels of this factor, it will spit out red, green, yellow, not red, green, or not red, not green, and missing. So it does have all those levels. It includes both the base levels and the coarse levels. The base levels will come first, and NA will also always come last. And then it also has this mapping matrix, which tells you how the coarse levels map onto the base levels. Okay, here's a better example. This is the example that I displayed at the beginning of my talk. This comes from a data set called Abortion 2000, which is included with the cvam package. This is the data set from the General Social Survey 2000. It has 2,800 rows and 16 factor variables. And if you tabulate it by the race variable and by the Hispanic origin, you just get that table that I displayed at the beginning of my talk. So now I'm going to show you how to create a combined variable with 4 base levels, the base levels that I wanted to set up: non-Hispanic white, non-Hispanic black, non-Hispanic other, and Hispanic, and carry along those Coarsened values. So this is a little bit detailed. I won't have to go, I don't want to exactly go line by line, but basically what I do is I use the add NA function, which then converts NAs to an extra level. So you can think of this as the Hispanic origin made into Hispanic, non-Hispanic, or missing as the levels. This adds that NA as an extra level to the race variable. And then this colon forms the crossing of all those. So it basically takes every cell in this table and makes it into a level. And so you do that. Then you have to create, you have to rearrange the levels so that the base levels appear first. You don't have to do that, but it helps a lot if you do. So what I'm going to do is I'm going to take this race Hispanic origin variable that I just created, and I'm going to set its levels to these values here on the right. And this Hispanic, what I'm telling it is that Hispanic is going to be a combination of these categories, Hispanic plus any race. And then I'm going to create my coarsened factor from this RH, and I'm going to give this levels list that basically tells the coarsened function that this level and this level are coarsened levels, and it tells you what the mapping sets are. And when you do that, you get this coarsened variable that is desired. So you get non-Hispanic white, non-Hispanic black, non-Hispanic other, and Hispanic. Those are the completely observed values in the base levels. Then you get 1,320 observations in this coarsened level, which is a combination of 1, 2, and 3. You have one observation in this NA white coarsened level, which is a combination of 1 and 4. And then you have no values that are completely missing. And if you print it out, you print out some observations, you see that you get the base levels, the coarse levels, and the mapping matrix. Now, there's a very lengthy vignette in my package that tells you, gives you a lot more information and many more examples about how to create, tabulate, and manipulate factors and coarsened factors. So I won't belabor this anymore. Okay, now comes the interesting stuff. Log linear models, as you probably know, describe the joint distributions of categorical variables. So it describes the distributions of a bunch of categorical variables and relationships among them. So it's a multivariate model for categorical data. And it models these distributions and relationships by linear expansions of log probabilities. And so I'll give you a little bit of notation. If you don't understand this, don't worry too much about it. It's not that important for the rest of the talk. But just imagine you've got a set of categorical variables to be modeled. I'll call that the vector of categorical variables, boldface V. Boldface little v is a possible value for this vector. So the possible value falls within the cross product of the set of possible values for the first one, the second one, up to the jth one. So this is the set of possible values, which is basically all of the possible combinations of the base level codes. So it's a J, you can think of it as a J-dimensional table. Those are the cells of the J-dimensional table are the possible values for this vector. Now, the probability associated with a particular cell is denoted by pi with that vector subscript. So pi sub v is the probability that variable vector, this multivariate vector v takes value little v. And the array of cell probabilities is denoted by bold pi. So bold pi is the array of all of these pi's over all of those cells. Now, if all of the variables were fully observed in a sample of n units, you could form the contingency table of frequencies, which I'll call bold case F. And bold case F has the same size and shape as this pi. So if this is a J-way arranged as a J-way table, this is the same, a table of the same, with the same dimensions. If you arrange this, string this out as a vector, this is a vector of the same length. And what I'm going to assume is that this table of frequencies has a multinomial distribution with parameters n and pi, where pi is that vector of cell probabilities. Now, a log linear model assumes that pi has the form log pi is equal to x lambda, where x is some known model matrix, and lambda is a vector of unknown coefficients. So this design matrix X is like a matrix of regressors, but what these are not, shouldn't be thought of as covariates or predictors in a regression model. What these are columns that are basically dummy codes and interactions defining related to what cell in the table you are. So the cell positions are encoded in these in the columns of this X matrix. And a log linear model is any model of the form log pi is equal to X lambda. Now, this is a funny kind of model because we know that the cell probabilities have to sum to 1. And because they have to sum to 1, there's a funny constraint, of kind of a nasty constraint on these coefficients. Now, in order to get around that, I'm going to use what some people call the Poisson trick. So to sidestep those sum to 0 or sum to 1 restrictions, I'm going to rewrite the model in terms of cell means. So if you think of mu as n times pi, that's the expectation of that frequency table, of those frequencies. I'm going to assume that the individual frequencies are distributed as Poisson and with cell means mu, and that the log of that mu vector is equal to x beta. So x is the same, but beta is now different. And this beta can now lie anywhere within the p-dimensional space. There's no constraint on this beta. And so even though the true model might be a multinomial model, that n might be fixed in practice, treating it as Poisson, estimating this model, but then going back and projecting the mu down into the pi space by just normalizing the mu's to sum to 1 gives you the same answer that you get from a multinomial model. The likelihoods translate, and the likelihood estimates translate over. All of the inference transfers over without any problems. So that's what I call the Poisson trick. So I'm actually working with a Poisson model, but I'm able to get cell probabilities and so forth out of it. Okay, to fit a log linear model, you call the function cvam. The first thing that you give it is a one-sided model formula. It's a one-sided model formula because the right-hand side gives you the variables that you're modeling, the joint distribution of, and that determines the columns of the X matrix. You don't have to code the X matrix. It will, R will create that automatically, just as it does in linear and logistic regression. It sets that up automatically. Data is an optional data frame that contains the variables. And there's also a frequency argument that can hold frequencies if your data are grouped. If you don't give a frequency, all the frequencies are assumed to be 1, and the data set is assumed to contain microdata with 1 observation per row. If you call cvam and the variables in your model formula contain missing values or coarsened values, cvam will handle them automatically. You don't have to do anything. It will compute estimates based on all the observed data. It's basically seamless. You would fit the same model using the same syntax, whether or not you have missing or coarsened values. You don't have to worry about it. The primary method is a maximum likelihood method using an EM algorithm, which I'm not going to go into the details of today. The documentation for the package has all the details. Okay, here's an example. Using the 4-level variable RH that I just created from that abortion 2000 data set, if you just say cvam and give it the formula tilde RH, you just give it one variable, it estimates the marginal distribution of that variable using all of the data, including the coarsened values. And then if you ask for a summary of the fit, you get some output. It tells you that there's 6 patterns of coarsened data, 4 cells in the complete data table, and so forth. It says EM converged after 31 steps, gives you the final log likelihood, gives you the estimated coefficients from the log linear model and their standard errors. Now, I don't know about you, but if you've ever worked with log linear models, chances are you've had a hard time interpreting those betas. I sure have. I don't even look at the betas usually. Instead of struggling to interpret those, I usually like to look at marginal and conditional probabilities implied by those betas. And so this package has a function called cvam estimate, which allows you to pull out marginal and conditional probabilities from the model. So if you say, I want the estimates from this model fit, the estimates of probabilities pertaining to that one variable that I have in my model, RH, it gives you the estimated probabilities and their standard errors, and those are computed by the delta method. So it spits out probabilities and standard errors. You could also ask for cell means if you want. In this case, probabilities or proportions are more probably more interesting. If you wanted to reproduce the results from the complete case analysis I showed you before, you can do it here. I won't belabor that. I'll just go on. So that's one variable with coarsened values. Here's two variables with missing values. Here's a small data set that came from the National Crime Survey. It's just two binary variables. V1 is whether you were victimized by crime at occasion 1. V2 is whether you were victimized at occasion 2. And because some people were, this is a longitudinal survey, some people were non-respondents at at wave 1, some were non-respondents at wave 2, and some were missing in both waves. So because of that, you get missing values in V1, missing values in V2, and some missing on both. There's two models of interest here. There's the independence model, which says V1 and V2 are independent. And then there's a saturated model, which allows them to be related. So here I'm fitting the independence model. I'm fitting the saturated model. And because you have group data, you have to give it the frequency. But it's just a matter of giving it two different model formulas. You have two different model fits. And now you can compare the fit of these two models using an ANOVA command. So here it tells you, by default, it does a likelihood ratio test, and it tells you that this independence model is rejected in favor of the saturated model with a very small p-value. If you wanted, in this case, you could get an asymptotically equivalent wall test by looking at the interaction term. So the association between these two binary variables is just a single coefficient in the log linear model. And the z statistic, if you square it, what you're getting is something which is basically the same as this likelihood ratio statistic. Okay, here's a better example. Let's go back to our abortion data set. Let's work with that coarsened factor RH, and let's pull three other factors from that data set. Let's pull out sex, which has 2 levels and no missing values. A 3-level political views measure, which has missing for about 6% of the sample, and a response to an abortion opinion question, which has levels yes, no, don't know, and refusals. And I'll treat the refusals as missing. So I have one coarsened variable, my race, Hispanic origin one, a completely observed one, and 2 with missing values. I'm going to fit a model that says I'm going to fit all 3-way associations between sex, political views, and race and Hispanic origin. And then I'm going to fit an association between that abortion attitude and each of these. Now, the reason why I like this model is this model implies a multinomial logistic regression for that abortion attitudes with main effects for political views, RH, and sex. Now, if you tried to fit that logistic model with conventional regression software, any record having a missing or coarsened value for any of the 3 predictors would be dropped. But if you embed this in a log linear model and apply cvam, all the available information is retained. So here I'm fitting this model. I'm setting up the, I take that model formula that I defined here, feed it to cvam, and then I also fit a saturated model, and then I can compare the fit using the ANOVA command. Now, this likelihood ratio test suggests mild lack of fit. but the p-value is not trustworthy because many of these estimated cell means are small. You can examine the cell means if you like. There's a function that gets the fitted values. You can also examine residuals. In this case, you'd have to look at something that I call quasi-residuals, which are analogous to Pearson residuals, but are available when you have coarsened or missing values. I'm not going to go into the details on that, but you can do the kind of residuals analysis with missing values and coarsened values that you can do with complete data. Now I'm going to show you a simple latent class analysis. Latent class models are an example of log linear models with missing values. So we can fit them, but you need to be careful because these have some unique features that cause them to behave differently from other types of log linear models. So here is a simple data set. It was published in this paper by Yang and Becker, which gives the results from 4 diagnostic tests for HIV infection. The 4 tests are labeled A, B, C, and D, and all 4 tests were given to a small number of high-risk patients, 428 high-risk patients. And so none of the tests is a gold standard. Any of them can produce false positives or false negatives, but we suppose that the
Oh, Joe, can I interrupt?
sure.
There's a question, slide 26. Is
Yes.
the likelihood ratio test valid for models fit with the EM algorithm?
Yes, because the likelihood ratio test or the EM algorithm is giving you maximum likelihood. So the ANOVA compares the likelihood achieved under the 2 models. And I didn't talk about prior distributions. You can also put in prior distributions, in which case EM will go to a posterior mode, and then you can do an analogous likelihood ratio test using the log posteriors. The vignette on log linear models explains that. But yes, it's the likelihood ratio test compares the 2 solutions.
Great,
Okay,
thank you.
so sure. Okay, so let's take these 4 indicators, none of which is a gold standard, and fit them by a latent class model. And in order to do that, you have to create a latent factor with 2 levels. So there's a little function called latent factor, which creates a variable, a categorical variable that has a given number of classes, but for whom all the values are missing. So I'm going to call that L. And then I'm going to fit a standard latent class model, which assumes that the 4 items are conditionally independent given this latent variable. So the latent class model says I'm going to fit the LA, LB, LC, and LD associations. So this is the model of conditional independence of A, B, C, and D given L. Now, when you fit this model, you get an estimate near the boundary, which is or on the boundary, which basically means some of the cell probabilities have gone to 0. That's extremely common with latent class models. It's nothing to be terribly concerned about. You can display the estimated class prevalences and item response probabilities using that cvam estimate command. So in this case, I'm taking the result of my model fit and I'm asking for estimates for the marginal probabilities for L, that latent variable. And that latent variable is completely missing, but you are estimating proportions in the population. And then the so-called item response probabilities, which are the conditional distributions of, or conditional probabilities for each item given the latent classes. And here's what you get. You see that you're estimating about 54% of the sample is in class 1, 46% in class 2. You see that class 1 tends to give positive responses to A, B, C, and D, and class 2 tends to give negative values for A, B, C, and D. So you can interpret A as the true positives and B as the true negative, or sorry, class 1 is the true positives, class 2 is the true negatives. So if this latent class model is reasonable, you're estimating the these rates of false positives and false negatives that are showing up in these item response probabilities. Okay, I'm running out of time here, so I'm just going to very, very briefly skim over the Bayesian capabilities in this program. So I am able to simulate values from an approximate posterior distribution. So if you regard the estimated covariance matrix coming out of EM as an approximate posterior distribution for beta, and assume, you say that it's multivariate normal, you can draw from that distribution using method equals approximate Bayes. So here I'm showing an example back to the crime data set where I'm fitting that saturated model and drawing from this approximate Bayesian posterior distribution 5,000 times, and then summarizing the results. I won't go into details, but that's pretty easy to do. I have a couple of versions of Markov chain Monte Carlo, which will draw from an actual posterior distribution for beta using Markov chains. There's two versions available. One is called a data augmentation procedure. One is called a random walk metropolis. If you're familiar with MCMC, those might mean something to you. If not, don't worry about it. But the output streams from MCMC are returned as objects that are recognized by the package CODA, which is a popular package for summarizing the output from MCMC runs. So it's easy enough to do that. You just say method equals MCMC, and then you can use control parameters to control how many iterations you want, length of a burn-in period, and so forth. And here's some diagnostics from the package CODA, which I'll skip over. You can also do multiple imputation. This package allows you to perform a run of MCMC and save simulated values of the complete data frequencies along the way, spacing them far enough to ensure that they are independent. And the number of cycles between imputations is set by the control parameter impute every. So in this example here, I'm going to perform 5,000 cycles of MCMC on the crime data, store the imputed frequencies at every 500th cycle, which will create 10 imputations. So you can do that. It just takes a second to run, and it gives you 10 imputed versions of the true underlying unobserved 2x2 table. So in this case, the multiple imputations are the imputed complete data table. You can also impute microdata if you like, and that's an extra topic which is covered in the vignettes. There's some other topics I don't have time to discuss today. It can handle structural zeros. It can handle cells with missing frequencies, as in capture-recapture problems. It has a few different prior distributions that you can select. It can also generate synthetic data, which is like multiple imputation, but wiping out the observed values and redrawing them along with the imputations. Finally, I will wrap up by saying that the next version, which will hopefully be out next month, will also, in addition to doing log linear models, it will do multinomial logistic regression with coarsened responses. So that allows you to fit models where the predictors can be continuous as well as categorical. So that's going to be a nice feature. Right now, the software does handle survey weights, but it does not give you correct survey standard errors. Correct standard errors are hopefully coming soon. They're planned for this next version. And I'm going to be doing it by Taylor linearization and also by replicate weighting methods. And finally, I'm going to include a feature for doing latent class regression with covariates and or distal outcomes. If you're familiar with latent class modeling, you probably know what that is. If not, you don't have to worry about it. It's just an extension of latent class analysis. And if you have any questions, feel free to email me. This is my email address. If you would like a copy of the slides, I'll be happy to send them to you. I'll correct a few typos and get them out very, very soon. I'm also willing, if you're to share the underlying paper that this talk is based on. It's being revised right now. But if you agree not to distribute it, understanding that it's under revision and you're eager to get going on it, take a look at it, I'm happy to share that with you as well.
Thank you, Joe. There's a question in the chat.
Yes.
Do you want me to read it for you?
I see it. Hi, Reggie. So what would be the limitation in terms of dimensionality? Okay, that's a great question. So this software does, it does form multiple copies of the underlying complete data table. So the complete data table cross-classifies all of the observations by all of the variables in your data set. And so if you have 20 binary variables in your model, you're going to have 2 to the 20th cells. So that can get pretty big. I have fit models pretty easily with, say, 15 variables. That's not a problem. But once you start getting more than that, that's a problem. That is kind of an inherent limitation in any software that does log linear modeling. But it's hard to get around that. I do code everything in Fortran, so it runs quite fast. And I have tried to optimize the execution speed, but in terms of memory, you're going to need a lot of memory to handle something that big.
Thanks.
Yeah.
And I will be emailing you for the slides.
Okay. I'll be happy to send them out.
Yeah, thank you for that question, because my question has a little bit to do maybe with dimensionality and maybe my misunderstanding or understanding of it. But it seems like manually the user has to kind of think about the coarsened levels and set those up ahead of time, right?
Yes,
and so,
exactly. Because
okay.
the user is creating the variables that go into the model.
Okay, so I guess just from a human standpoint, if there was, a whole bunch of combinations like that, it'd get unwieldy pretty fast trying to.
Right, but that's not, that's part and parcel for analyzing data where you're combining items on a questionnaire to form new variables. So anytime you do that, you have to worry about, well, what will a missing value in this variable do to my composite variable down the road? So those are questions that you're going to have to deal with no matter what. If you have just a plain old categorical variable with missing values, you don't have to do anything. You just stick it in the model and it runs. But you only have to do something special if you do have these coarsened variables popping up, coarsened values popping up in your variables. You have to define what the coarsened levels are. But once you do that, all of that is carried seamlessly into the models and through the models, through the output and everything, and you don't have to do anything after that.
Yeah, no, and it seems, I mean, I think that's like you said, a typical problem. It's not something that's it's a limitation no matter what you do, right? Or
yeah, I mean, people always collapse categories. If you have a detailed race variable with 63 possible levels, it's very you're probably going to collapse that down anyway, and then you're going to have to figure out, well, if you have some information where you know that this person sometimes identifies as white, but you don't know of anything else, you're going to have to figure out what to do with that. So this kind of thing comes up a lot when you're analyzing data, say from when you're pooling, say, data from surveys with administrative records and so forth. You're going to have items that are coming at you with different levels of granularity. And so this is going to happen a lot.
Yeah, that's a really good point. You made that at the beginning. I forgot about harmonization. Yeah. Thank you. There's another question in the chat. I'll read it. Can the package handle different coarsening mechanisms? What happens if one variable's coarsening is dependent on another variable's coarsening?
That's a good question. So you'll notice that I specify the model in terms of the underlying true variables. So the log linear model is applied to the true variables, and you don't specify anything about the coarsening, which you don't have to if the coarsening is coarsened at random. And now coarsened at random means that the probabilities of coarsening don't really depend on on anything that you can't see. It doesn't mean that it doesn't depend on the data, the true data. It depends on, it just can't depend on anything that you can't see. Now that's a hard thing to wrap your mind around. It's hard enough with missing data. Missing at random can be pretty hard to imagine what it means in a multivariate data set. Coarsening at random is even more difficult. And so if you look up very few references that have been, a few papers that have been written on what coarsening at random actually means, it's really, really hard to even understand what that means, let alone come up with a coarsening mechanism that makes sense when it's not controlled. Generally, if you're dealing with things that are values that are coarsened basically because of, like say, subsampling in the GSS example that I have, you don't have to worry about it at all. Coarsening at random will hold, but coarsening at random may not hold in other scenarios. We really don't have a good handle on what an alternative to that might be at this point. Now this, having said that, I will qualify it by saying that if you are willing to define additional variables that correspond to missing value indicators, or missingness indicators. So for example, here is, imagine that you have two data sources. You have one data source where you're recording variable 1, another data source where you're recording variable 2. You have some people that are in data source 1, some that are in data source 2, and some that are in both. You can define another indicator variable that says whether or not you're in source 1. You can define another indicator variable whether or not you're in source 2. Now you have 4 variables. You have the 2 variables of interest plus the 2 indicators for being in or out. You don't know how many people are in that out cell. So that becomes what you call a hidden cell or a missing frequency. You can fit models to that, and that falls under the heading of those capture recapture models. Now, I didn't have time to show you that today, but when you look in the new, if you download the new version of this package next week, there will be some information on that. So there will be some examples of that. So in certain cases, you can include missingness indicators, which are a kind of coarsening indicators. You can include those in the model. Now, you won't be able to estimate a saturated model. There are limits on what you can estimate, but you can fit some simple log linear models to that. So I hope that makes sense.
Yes, I think it does make sense, at least at this point in time.
Yeah, and so we have a small group at the Census Bureau that's starting to look at these types of log linear models for dual system estimation, for multiple system estimation. That's kind of exciting.
It is exciting, very, very interesting. And so that's a great teaser for accessing your package next week. So we'll have to see how many downloads you get, right?
Yeah. Now the package, you can download the package right now. It won't have. There's a few features in the new one that won't be in the one available right now, but people have been using the one that's currently up. So I know somebody at the Italian Statistical Bureau, ISTAT, has been using it. A person who I recognize who's well known in record linkage. He says the package is useful, and so I'm happy about that. I have at least one fan out there. But I do know that it has been downloaded quite a few times.
Well, that's great. That's good. But you're talking about the new and improved one that's next week, right?
Well, he's been using it for quite a few months now. So, I mean, it's been some versions of the package. Every time I find a bug, I post a new one, and it's been available for over a year. And so I haven't checked the number of downloads, but it's been downloaded hundreds of times.
Oh, great. Okay, I don't even have my first package, so you're way ahead of me. All right. Well, any other questions for Joe? Well, thank you so much. I'm going to turn my camera off just so I can tell you to your face. Bye. Thank you so much for being here today. And
Thanks, Joe.
Yeah, thank you.
It was a fantastic talk. Thank you.
Thanks. Yeah,
All
so about the slides, should we just say that anyone who wants the slides, just contact me and I'll send them right out?
Yeah, that would be fantastic. Or, they could contact me too, and then I'll contact you.
Okay, I'll be sure to send them to you as well.
Great. Okay. All right. Thank you. Thanks again, Joe. And thank you, everybody, for
Thanks, Joe.
for being
Bye.
here.
Great to see everyone. Bye.
All right. Bye.